Welcome back everyone, this is Mr. Dukar here, and so today we're going to be talking about how to find the charge on ions using the periodic table. So far we've been talking about how to find the charge on ions using Bohr model atoms. And so I'll do a quick recap of that here, but I've also done a screencast of that in the past that I'll want you to take a look at, and you can see that right here. There should be a link right there where you can see previous screencast if this first part confuses you, but let's take a look right here. So for this atom to become stable, this is beryllium right here. You can draw the Bohr model atom as I've done, and then you say, well, let's imagine what this atom does to become stable. Think of a number line from 0 to 8 where the atom is going to gain or lose electrons to get to that 0 or 8 when we're talking about the number of valence electrons. So in this case we're starting with 2 valence electrons, and for the atom to become stable it's either going to gain 6 or lose 2. The atom always does the thing that is the least amount of work, the least amount of steps, all things being equal. So in this case the atom is going to lose these 2 electrons right here, and then we want to keep track of how many positive and negative things the atom now has. So if we think about how many positive things does this atom now have, well, it's got 4 positive things. How many negative things does this atom now have? Well, it's got 2 negative things, and so what's our overall charge in this atom going to be? It's going to be a +2 or a 2 plus, and so the way you would write this is just Be 2 plus, like that. So we are going to build on this, and I do want you to notice what that charge is, because I'm going to show you another example, and then we're going to find them on the periodic table and look for the pattern. So let's get started. And if we do something similar with magnesium, we'll find that, notice that magnesium has 2 valence electrons, and so when we do the math, it's got 12 positive things, plus now if we lose 2 electrons, then that means it now has 10 negative electrons when it becomes stable. And so you're just adding up the number of positive things and negative things, talking about protons and electrons, of course, that the atom now has to find its overall charge. Well, it turns out that that's going to end up being a +2 charge for magnesium as well. So magnesium and beryllium both have a 2 plus charge. So you might ask yourself, is that a coincidence? And the answer is no. Let's take a look and see where they're at on the periodic table. Alright, so the important thing to note is right here, beryllium is going to be right here, and magnesium is going to be right under it. So that's where these 2 atoms are found, and they both have a +2 charge, and you could say that they both have 2 valence electrons to begin with as they begin as atoms and transition into ions. And so that's not a coincidence. In fact, if you say these have 2 valence electrons, it turns out that if you look at any of the atoms in this group or family right here, they all have 1 valence electron. Here they all have 2, and then we'll just ignore these for now. These are transition metals, and they don't follow this pattern. They're a little wackier, a little more difficult, but we're talking about the number of valence electrons now that each of these atoms have in these vertical columns here, which are called groups or families. Pretty amazing that this level of regularity is in the periodic table, or you could say pretty amazing that we have this level of regularity in our universe, actually. So 6 valence electrons here, 7 valence electrons in this column, 8 valence electrons in this group or family right here, going up and down right here, with the exception of helium. So let's see what we can do with this information. Okay, and what we can do with this information is think about what the overall charge is going to be. If we have something in this first group or family right here with 1 valence electron, let's think about that. If you have 1 valence electron, 1 electron in the outermost shell, that atom is going to lose that electron, and then overall, if you lose a negative thing, you can think about this mathematically and say you end up with a +1 value, or you can just say to yourself, I now have one more proton than electron. And if that's the case, then if something has 1 more proton than electron, that means it has an overall +1 charge. Well, that's true here. This is going to be +1, and it's true for the next group or family over, the alkaline earth metals. If you have 2 valence electrons, which is true here, this is going to be a +2 charge. Turns out that this will be a +3 charge right here. Turns out these over here, if you think about this, this will have no charge right here because these are already going to be stable. These noble gases are already going to be stable. If we work backwards, it's a little bit easier. And this group or family right here, the halogens, they want to gain 1 electron to become stable. And so we're going to call that a -1 charge. Everything in that halogen group is going to have a -1 charge. And so it's just a very cool pattern that you can see emerging here. Now these with 4 valence electrons are not going to have ionic bonding. They're not really going to form ions typically, and so we're just going to ignore that for now. If you wanted to say it's plus or minus 4, I suppose you could, but in reality that's not what happens in nature. Alright, there's one exception I want to point out here. This exception is helium. It is stable with only 2 electrons in total, and so it doesn't follow the 8 valence electrons pattern, but it is following the pattern of being stable, having filled outermost shells. So this is really important information I want you to be aware of. If you think about this, this is one of the most key ideas in early chemistry, is how many valence electrons you're going to be dealing with, and based on that, what the overall charge for these ions is going to be. So thank you for listening. I hope you've enjoyed it. And if you have, please throw me a like or a comment. Thanks.